Welcome. In this demonstration, we're going to look at the test of significance for linear regression. So what I have for us is the grocery store data that we've worked with in the previous demonstration. And I've already calculated the total gross margin in column I, which is the gross margin percentage times the total sales. And what we're going to do is use the total gross margin as our response variable. And we're going to use all of the possible predictor variables in our linear regression. So we'll include zip code, number of purchase visits, user's credit card, and microvision. The first thing I want to point out is that we're using the adjusted R-squared to evaluate as one of our evaluations of this linear regression. And just as a reminder from the previous demonstration, we're doing that because the adjusted R-squared takes into account both the sample size and the number of predictor variables. Most importantly, the number of predictor variables. So if we have one predictor variable, then we would just use the R-squared. But we have multiple, as can be seen down here. We have 4 predictor variables. And so that's taken into account here. So we can say, based on the adjusted R-squared, that the predictor variables, thus this linear regression equation, accounts for 38.31% of the variation in the total gross margin. This demonstration is primarily about test of significance for linear regression. So the first one we want to look at is the significance of F, which is right here highlighted for you. Now, what we're looking at is joint significance here. So this applies to the entire equation. And it's based on a two-tailed hypothesis. So let's take a look at that hypothesis. It will help to have a visual. We begin with a null hypothesis. And in the hypothesis for joint significance, the null hypothesis, like all null hypothesis, is from the point of the extreme critic and says, well, you're not going to prove anything with this. So we set each of the coefficients equal to one another, and all of that equal to 0. So what we're hypothesizing is that these values here will be 0. That's our null hypothesis. This equation has no impact on the predictor variable. Then our alternative hypothesis is that at least one of those, this BI, is not equal to 0. We're evaluating the hypothesis for joint significance based on a specific alpha. So the alpha equals something. And the alpha is the allowed probability of making a type 1 error. So rejecting the null hypothesis when it's true. We're willing to risk that at a certain level. And this is based on our confidence levels, right? So we typically work with 99% confidence level, which would give us a 0.01 alpha, or a 95% confidence level, which would give us a 0.05 alpha, or a 90% confidence level, which would give us a 0.1. Now, those are just the norms, right? And if you recalled earlier, when we were setting this linear regression up, we could have adjusted the confidence level and therefore adjusted our alpha. But I've left it at 95% for our confidence level. Therefore, our alpha is at 0.05. And so what we're looking for is the p-value. So in this case, this significance level here, our p-value, is less than the alpha, then we can reject the null hypothesis, remembering that, well, we run the risk of a 5% chance of a type 1 error here because we have an alpha of 0.05. But because the significance of f, the p-value, is less than 0.05, we can reject the null hypothesis and say that at the 5% significance level, the predictor variables are jointly significant in explaining the response variable. Now, obviously, if this was greater than 0.05, then we would have to accept the null hypothesis and say that this group of predictor variables, remember this is joint significance. So if it was greater than 0.05, we would have to conclude that they are not jointly significant in determining or explaining the response variable. Let's talk about the hypothesis for individual significance. So when we look at the coefficients here, we can go to the right and look at the p-value for those. And it's similar to the hypothesis for joint significance, but of course we're only working with one coefficient at a time. So let's take a look at that formula. So the formula for the hypotheses for individual significance, this being a two-tailed illustration, is that whatever that coefficient is, we're saying it's going to equal 0, meaning that it's not going to play a role in explaining the variation in our response variable. So the null hypothesis is that that coefficient equals 0. Well, the alternative hypothesis is that it doesn't equal 0. And we're applying that hypothesis to each one of these. And then based on that, we have a p-value that's calculated. And just like for the hypotheses for joint significance, we're using an alpha in our hypotheses for the individual significance, and it's the same alpha. It is based on our confidence level. So in this calculation, linear regression output, we have a confidence level of 95% and an alpha of 0.05. So what we're saying is that as we look down this row here on the coefficients and look down the p-value, that we can say the number of purchase visits has a p-value less than our alpha of 0.05, and therefore it is significant as a predictor variable in explaining the response variable. But zip code has a value that is a p-value that's greater than 0.05. So in that case, we would have to accept the null hypothesis and say that zip code doesn't explain in any significant way the response variable. Let's talk about the two-tailed nature of this. It's two-tailed because we're saying that that coefficient is not going to be equal to 0. It can be either negative or positive. But there are situations where we would want to use a one-tailed test here. And it might be something like uses credit card. Maybe we want to determine if it's above a certain amount. So we have some threshold based on our credit card expenses. And if someone switches to a credit card, will switching to a credit card increase each purchase by $100? So if we're doing a one-tailed test for individual significance, we would use something like this. Uses credit card is less than or equal to 0, or uses credit card is greater than 0. Now, I mentioned the example of 100, and we could plug that in here as well. So uses credit card is less than or equal to 100, uses credit card is greater than 100. And those things would change our p-value. Notice that I picked 100, and in this equation that uses credit card, the coefficient is 77.98. Now, once we switch to a one-tailed test of significance, the formulas change for us. And this is important to realize because when you're doing the automated formulas from the data analysis tool pack, Excel does a certain type of formula. In fact, it does the calculation for the two-tailed test. We can demonstrate that with a formula for the t-distribution. Now, this formula is what calculates this t-stat right here. And what's important to recognize is this variable beta j0. So this is the hypothesized value. It equals 0, or it's less than some value or greater than some value. And so normally when we're doing a two-tailed test, we plug 0 into this, so the equation is simplified to simply b sub j divided by the standard error. Now the standard error is right here. But once this beta value increases to anything, changes to anything other than 0, this formula and the results change. And that's why in Excel, when you have that situation, you have to manually calculate, well, using the functions, not using the data analysis toolpack. You have to use the t-distribution calculations for either the left-tailed or the right-tailed calculation. So let's take a look at doing that. I'm going to adjust my spreadsheet a bit to create some room so we can do these calculations. And we're going to get rid of these values because we'll use this space to do our calculations to illustrate what we're doing here. Now, what I want to show is what our HA is, our alternative hypothesis. And I am able to adjust this. I'll show you how to do it. We can go down here and make this a subscript, so our alternative hypothesis. And we're going to start out with a 0. Now, I know as I do these calculations that I'm going to need the degrees of freedom, and so I want to calculate those here. So do degrees of freedom equal, and let's just right justify that to allow it to line up. And my formula for that is n, which is my count, minus k. Now k is the number of these predictor variables that I have. So we have 4 here, minus 1. We're going to use B14, which is our count, minus B12, which is the number of predictor variables we have, minus 1. And so we have our degrees of freedom there, and we'll use that in our formulas. So first, let's calculate that t-stat, this value right here, with our using a two-tailed test. And so we'll use this here. And the formula that we're going to use is simply that formula that we had looked at previously. And I think I'll just put it back up here just for the sake of illustration. All right, so what we're saying is that it equals my value, which is there, my b sub j, minus my hypothesized value, and you can see how when that's a 0, it simply goes away, divided by, and this is that standard error, so it would be here. Now I'm going to modify, I will be copying this formula down, so I'm going to modify this so that that hypothesized value stays the same. And then let's just reduce this down to our 4 decimal places, and you can see that it matches, and when we copy it down it should indeed match all of those values, and we do. Now this lack of a line always bothers me, but you don't have to obsess over that. I just like things looking nice and tidy. So there we go. We've calculated the t value. Now I'll just put it up here. This is my t stat. Now what I want to do is I want to do the p-value, which would be this value right here, to illustrate that. And we're going to do it for the two-tailed. We're going to do it for a left-tailed, and we're going to do it for a right-tailed. So let's enlarge those a bit. So as a reminder, the two-tailed has an equal sign here in the hypothesis. So notice that when I want the equal sign to display, I have to put a single quotation before it. That allows Excel to interpret it just as the equal sign. Otherwise, when I type equal, it expects a formula. And I'll do that as well with the less than and the greater than signs, which are the signs that we used if it's left-tailed or right-tailed test that we're doing. So let's do the two-tailed test, and what we're going to do here, well, I want to illustrate something, so this is a little bit odd, but I'm going to do it here first, equals my t distribution. Now it's two-tailed, so that's this 2t, right? So we're going to do that. Now x is my t-stat, so that's the t-stat there, and then I want my degrees of freedom up here, and since I'm going to be copying this, I'm going to make it an absolute reference. And you'll notice, well, you'll notice it matches, although it's a 0, so it's not as helpful as it could be to show the matching. But here's what I want to show. When I drag it up, watch what happens. I get this error, right? Now, why would I get an error? Why would it not just match this 4908? Well, the problem is that this formula expects a positive value for the t-stat. So if the t-stat is negative, I have to make it positive by putting a negative sign there. And I can change the number of decimal places so it matches. So notice I have 0.4908, 0.4908. Now, here's the problem. The problem, if I drag this down now that I have it negative, it's going to work for the negative numbers, but not work for the positive numbers. And I could certainly come in here and manually take out this, but that's not the right way to build a mathematical model that you want to be able to reuse. You want to share it with someone else. Maybe that someone else you're sharing it with is your future self. 6 months from now, when you come back to this, you've forgotten that detail. And that happens. So let's talk about how to fix this and fix it the right way. We're going to use an if statement inside of this. So instead of just looking at F20, we're going to say if F20 is less than 0, we want a negative F20. Otherwise, we want just F20. And it should work. And now when I copy it down, it should work as well. And it does. It matches all of these. So this is what Excel is doing by default with the data analysis tool pack, the linear regression and the t-test or t-stat and the p-value for that. It's using the two-tailed. Now watch what happens to that calculation when I change my hypothesis. So currently my hypothesis says that equals 0. Right? So this would actually be the null hypothesis, would be that it equals 0. The alternative hypothesis would be that it doesn't equal 0. So I should probably have a doesn't equals sign there. So I'll just change that to not, because there is not a convenient way to show the symbol for a not equals sign here. So we'll just say not equals to fix that. All right, so what we're saying with the null hypothesis, or I'm sorry, the alternative hypothesis, is that we hypothesize that these coefficients do not equal 0, and then all of our calculations work and match what Excel has calculated. Now notice what happens to this when I change it to a 1. Not equal 1, well now all of my two-tailed p-values have changed. In fact, they're all significant at the 5% level. They're all significant. So when we're adjusting this to some other value besides 0, we have to build that into our Excel work, our Excel formulas, by manually calculating the t-stat and from that the two-tailed test. Okay, to do the left-tailed test, it is the t.dist. That is the one that is left-tailed. Oops. And I need my x, which is my t-stat. I also need my degrees of freedom, and I'm going to make that an absolute reference. And in this case, I need to select cumulative, so we'll make that a 1. And this gives me my left-tailed p-value for this particular t-stat. And I can do that for all of these. And now let's do the right-tailed, and then we'll talk a little bit more about these. The right-tailed is the dist.rt for right-tailed. And again, we need that t-stat. And again, we need the degrees of freedom. Notice that the left-tailed is the only one that's either cumulative or not. Okay. And finally, we'll fix all those because it is good to be nice and orderly. Okay, so now remember the left-tailed, we're saying that it's less than, so, and in the right-tailed, we're saying that it's greater than. So let's pick a value of 1 here, and you can see what happens to this. So when we look at the p-value for the left-tailed and the right-tailed, and remember what we're trying to determine is at the 5% significance level, are these individual predictors significant in explaining the response variable. And so what's interesting here by selecting 1 is we can take a look at this and take a look at the coefficient. It's 0. And this is saying, well, if it's less than 1, is that significant? It kind of makes sense, right? So our p-value is less than 0.05. So we're saying, yes, that this one, that was zip code, this one is significant at the 5% level. But if we're saying greater than 1, then it's not. It's got a p-value that is 1, which is obviously much higher than 0.05. And notice that these down here, we can do the same thing. This is at 33, and intuitively, right, it makes sense that it's saying that, well, it's hypothesized that it's less than 1, and so, no, that's not significant for this left-tailed t-test. And here, it's hypothesized that it's greater than 1, and so, yes, that is significant at the 5% significance level. And we can follow these down the same way. This one, less than 1, all right, it's a negative 0.27, so it is significant. And here, greater than 1, it's not. Now, I caution you not just to look at these and come up with your own answer for whether it's significant or not, but this example nicely illustrates what happens here. You really do need to calculate these out. And it's a great way to learn, to remind yourself about a two-tailed test, a left-tailed test, a right-tailed test, remind yourself about hypothesis testing, and integrate that with significant tests for your linear regression. So now it's your turn to try.